The cathode is a vital component of lithium-ion batteries because it represents lithium-ion's primary and active source. Moreover, as graphite represents the choice of the anodic side in the commercial application, the cathode selection actually determines the cell's final characteristics. In this lesson, we'll briefly describe the feature of cathodic material. The cathode stores lithium ions through electrochemical intercalation, which requires suitable lattice position for insertion and reversible release of lithium ions. Lithium ions are reversibly introduced and removed from the cathode and anode material during charge and discharge cycles. The design of materials for positive electrode must account for all these aspects, including suitable structure for ion insertion and desertion, transition metal center, capacity, operating voltage, cost, and safety. In detail, in the desirable characteristic of cathode material, one should include robust crystalline structure, layered or open framework, able to relax upon insertion and the insertion of lithium ions. High lithium content with lithium ion placed onto accessible site. Suitable operating potential with good compromise with high potential, maximizing the energy density of the cell and the electrochemical stability of the electrolyte component. High capacity related to high lithium content to maximize the cell's energy density. Thermal stability to withstand with temperature without decomposition, thus guaranteeing the safety of the device. Low cost related to the use of abundant and non-critical materials. Considering this point, it's possible to understand the evolution and diversification of commercial cathode materials since their first appearance on the market back to the 90s, and also outline the possible future evolution, as we'll see at the end of this lesson. All commercial cathode materials share a common feature. They are crystalline oxide with a layered structure and an open structure, presenting channels for lithium diffusion. Let's examine each of them in detail. Lithium cobalt oxide, LCO, is one of the first commercial cathode material. Thanks to its excellent electronic conductivity, it's known for its energy density and rapid change capability, which are intrinsically related to the layered structure. However, LCO has limited thermal stability and relatively short cycle, 500 to 1000 cycles, due to structural degradation over time. This limits its use in large-scale applications such as electronic vehicles, while still finding application in portable devices. To mitigate the drawback of LCO, a new class of material has been developed, nickel manganese cobalt lithium oxide, NMC, and nickel cobalt aluminum lithium oxide, NCA. The partial substitution of cobalt with nickel and manganese combines higher experimental capacity values, improved chemical stability and thermal stability, and a good balance between energy density, power, and lifespan. Similarly, NCA can increase stability, resulting in long life and high specific energy. These materials represent a benchmark, especially in the transportation sector, holding the largest market share, but still face significant problems, including chemical instability during cycling, high cost, and the need for an adequate thermal management system. Drawbacks are driving the search for alternative high-capacity cathode material. Key factors fueling innovation include energy density, crucial for storing more energy in smaller, lighter batteries, important for electronic vehicles, aiming for longer driving ranges, and for portable electronics. Thermal stability, enhancing this is critical to prevent overheating and improve battery safety, avoiding risk like thermal runaway. Research focuses on materials that maintain high performance and long cycle life, while reducing thermal risk. However, in addition to pure performance, the development of new material for electrochemical devices must satisfy mandatory requirements, addressing cost and sustainability, issues that become increasingly important daily. The extraction and processing of raw material significantly contribute to the overall environmental footprint of battery production. Hence, developing more sustainable material alternative is crucial to reducing reliance on scarce and expensive resources while promoting eco-friendly battery technologies. Regulation and consumer demand for greener solutions are pushing industries to reconsider material choices, ensuring that future batteries align with principles of sustainability and circular economy. In particular, the expensive use of cobalt in the current commercial standard like NMC or NCA poses ethical and political concern, since cobalt commodities have reached limited availability, are expensive, they are harmful to human health and to the environment. Cobalt mining is often associated with exploitative labor conditions and significant ecological damage, reinforcing the urgency to develop cobalt-free or cobalt-reduced alternatives that maintain high electrochemical performance. Researchers are exploring several promising directions to tackle these challenges. One of the most advanced approaches involves high nickel cathodes, which minimize cobalt content while maintaining high performance. However, this rush for cobalt removal has inadvertently increased in the demand for nickel, the following critical raw material in line. Another promising avenue is developing cobalt and nickel-free cathodes using abundant and low-cost elements like manganese or iron. These materials provide a more sustainable and cost-effective alternative while maintaining good electrochemical performance. Lithium manganese oxide (LMO) has been developed as an alternative to layered system and offers an economical and eco-friendly option with good thermal stability. However, it faces challenges such as capacity fade during frequent cycling, lower capacity and lower electrical conductivity concerning the layered material related to its spinel structure. Innovative strategies such as dual doping technique can improve the stability and performance of LMO. Lithium iron phosphate, LFP, is a polyatomic structure with improved chemical and thermal stability, thanks to which it prioritizes safety and stability. At the same time, it provides lower energy density compared to the other cathode material. The absence of critical raw material, except for lithium, is safely and maintaining a good compromise with energy and power density, make LFP the emerging chemistry for commercial application. Researchers are also exploring new ideas, like lithium-sulfur battery, which could significantly enhance energy storage capacity. However, they still encounter challenges related to long-term stability and cycle time. Solid-state battery, which replace liquid electrolyte with solid alternatives, could be a game-changing breakthrough. This innovation enables more stable and safer cathodes while increasing energy density and allowing for faster changing. Leading companies and research institutions are actively working to bring this technology to market to revolutionize energy storage. Simultaneously, considerable efforts are underway in battery recycling and material recovery. Modern recycling techniques enable the efficient extraction of lithium, nickel, and other valuable elements from used batteries, minimizing cost and environmental impact. In conclusion, the future of battery relies on integrating this innovation into scalable and commercially viable solutions. Ongoing research is paving the way for the next generation of more powerful, safer, and environmentally friendly batteries, ready to transform the energy and transportation industries.